We'll wait for others to join. So welcome everyone to week 12 tutorial for the course Fluid Mechanics. So I hope everyone has been very regular to their assignments and are ready for the exam. Hope most of you have done all the preparations so far by now. Exam is near. And this is the session where we have discussed so far up till the Venturi meter. In the last tutorial, we have completed with the Venturi meter, where we were dealing with the applications of Bernoulli equation, discharge measurement, velocity measurement, pipe flow, free jet flow, or free vortices. And in discharge measurement, we were talking about the Venturi meter. We have understood the concept behind the Venturi meter, and we have to start the derivation of the discharge equation of the Venturi meter. So let me just share my screen. I hope everyone is getting all the notes and PDFs. Those who have missed any of the tutorial, they are able to watch on my YouTube channel. So I guess from the NPTEL team, every week you get, after the tutorial, you get the a sheet, Excel sheet or Google sheet, where all the links corresponding to my name, Varnit Kapoor, you will see all the links of the tutorial for the course, as well as a link to the Google Drive. And those who are new also, so my YouTube channel name is NPTEL with Varnit. So I expect everyone is able to observe, and in each video you can find video description, you can find the PDF notes for the Google Drive link for the PDF notes. Okay, I think now my screen is visible. Yeah, great. Okay, so visible. So let's start. So let me write discharge. I hope I am clearly visible and audible. Okay. Discharge equation for Venturi meter. Okay. So let us first frame a diagram of a Venturi meter, and let us make a general diagram where we have converging section, a throat section, and a diverging section. Okay. I think there's some. Okay. And this is generally a reference. So let us say the flow is happening like this, with the flow rate Q, which we want to estimate. Okay, and let us assume a point 1 here, which has a distance of Z1 from the base, that is Z1. Okay, and a point 2 here, that is at the throat section, let us suppose. So at this point, okay, so this position is Z2, let us suppose that. Okay, and suppose we have a piezometer, which is from where we are getting our heads. So let us suppose piezometer here is from here. You are having some head value, okay, that is P1 by W plus Z1, okay, piezometric head. And similarly, if you have a piezometer at this position as well, you are having some head that is P2 by W plus Z2. And the difference between the levels of the head is there as well. So this head should be a much bigger comparative to the other, because pressure will be high at this position compared to the. So let us say it is still here. So this is your head value. Difference between this level and this level is your head pitch. Okay, the head pitch. Okay, so flow rate is Q only, outside also it is Q, which is happening. The flow is going like this. Okay. Then divergent. Okay. Yeah. Okay. So if we apply the Bernoulli equation between the point 1 and point 2, what will happen? So if I apply the Bernoulli equation, let us make this to the target to the center. I hope this will be better. Yeah. So let us, so that is P1 by W, Bernoulli equation between 1 and 2. So that is P1 by W plus Z1, that is your hydrostatic pressure, plus the dynamic head V1 square by 2G. Okay. So let us say the velocity here in this section is V1 at point 1, this velocity is V1, and here the velocity is V2. Eventually the velocities will be different, okay, in the Venturi meter. So it is P1 by W plus Z1 plus V1 square by 2G is equal to P2 by W plus V2 square by 2G. So fluid is same, that is why it is W only, okay, plus 2G plus some losses will also be there, as we have studied the Bernoulli. So if you rearrange them, take the V1 to the left hand side, and if you observe that both P1 and P2 are both same or different. So if I say my whatever the P1, P2 different will be there different. So let us say, oh, sorry, I think I missed one term here, plus Z2, and this is Z1, plus V2 square by 2G, plus some headlands, okay? So if I take out the V1 square by 2G common to the left hand side, so I'll get V2 square, V1 square minus 1, and this head and this head difference comes out to be H, let us say H minus HL. So it will be H minus HL if you take out like this after rearranging, where H is your piezometric head, as I have told, marked here in the orange. So H minus HL, sorry, in the yellow, H minus HL. So H is your piezometric head. I'll again write piezometric difference. Okay. So from here, you will get V1. That is nothing but, if you see, A1 V1 is equal to A2 V2. Okay. So you can write V2 as what? What we can write? V2 by V1 ratio will be how much? A1 by A2. So since I'll write here, since A1 from the continuity, A1 V1 is equal to A2 V2. So this implies V2 by V1 will be A1 by A2. So put this value here. Okay. So if you put this here, so from here you will get the V1 value to be A2 into root of 2G H minus HL by under root of A1 square minus A2 square. So this is your actual velocity. This is your actual velocity. Actual velocity. Actual velocity. So from A1 V1, if you put this V1 here, what you will get? So A1 V1 A1 A2 root of 2G H minus HL by under root of A1 square minus A2 square. Okay. A1 square minus A2 square. And A1 V1 rho AV is nothing but your flow rate. Okay. So your final Q actual will be A1 A2 root of 2G H minus HL by under root of A1 square minus A2 square. That is your actual flow rate. Okay. If I say my losses are 0, then that means my HL will be 0. Okay. If my losses are 0, if losses are 0, this implies my HL is 0. Then what will be Q theoretical? It will be theoretical, because in reality and actuality, there will be losses. But in theoretical sense, it will be A1 A2 root 2GH by under root of A1 square minus A2 square. Okay. This is your theoretical. Okay. So what will be actual now? So here we will come across with one term. So from theoretical, if you want to get an actual, we need to multiply it with some factor. That is the factor CD, coefficient of discharge. That is Q actual by Q theoretical. So this implies your Q actual will be CD times, if you multiply the Q theoretical, this one, A1 A2 root 2GH by under root of A1 square A2 square. So this is also a Q actual. Both are same eventually. Both are same. These both terms are same. Okay. So this is your CD, that is coefficient of discharge. Coefficient of discharge. Okay. Coefficient of discharge. It is ratio of actual to that of theoretical. So if I want to write in terms this, if both are equal, let us compare both are equal. So from here we will get the CD value also. So that is CD A1 A2 root 2GH by under root of A1 square minus A2 square is equal to A1 A2 root of 2G H minus HL by under root of A1 square minus A2 square. So from here you will get your CD as under root of H minus HL by H. So this is also your CD expression. Okay. CD expression. All right. Other thing, if you observe, so if you are given in the question only the heads value, right, and loss value, it's asked that what is the value of CD, you can get immediately like this. Okay, for the venturimeter case. So if I see, since my Q theoretical was what? A1 A2 root 2gh by under root of a1 square minus a2 square. This was my theoretical. So if I multiply, this is my what value? This is my Venturi constant, let us say. This is not your CD. It is Venturi constant into the root of h. Okay. So this is all. If directly Venturi constant value is given, no area, anything else is given, it will be, the expression will be like this. So this is your Venturi constant. Okay, Venturi constant. So what will be Q theoretical then? Then Q theoretical will be CD times, sorry, Q actual. Q actual will be CD times Q theoretical. That is nothing but CD times C into root of H. Okay. So if you put this here, this will be your Q actual. So Q actual is CDC root of H. Okay. I think this much is clear now. Okay. So we understood the expression for discharge value. We have got our discharge for the Venturi meter. And this can be related in very different ways. Okay. Now we'll come to the topic of relation between piezometric head and manometric deflection. Okay. So there can be some scenarios where if you are the fluid is flowing through the Venturi meter, there can be a scenario where the head can go at the converging section up to like 40 meters. So you cannot put a piezometer of such so huge length. That's why when we understood the pressure measuring devices in that chapter, we dealt with manometers for high pressure differences. Okay. So in such scenarios, like if I have a Venturi meter like this, okay, so with that some datum, suppose. So here it will be Z1, and let us suppose here it is Z2. Let us suppose that it is a bit inclined or whatever it is, or both are equal, doesn't matter. But we are saying at 0.1 and 0.2. So again, flow is happening from here. Fluid is flowing, and we have a piezometer attached at this point, and we have a piezometer attached at this point. Okay, here my pressure head is higher, piezometric head is higher compared to this. But suppose if this value, piezometric head is up to, the piezometric head difference is up to like 40 meters of difference is there. You cannot have such a huge if very high. Then what you do in such scenarios? You convert this into a manometric. You attach a manometer compared to the piezometer here. Okay. So now my Venturi will be like this. Okay. Now it will be attached to a manometer. So let us say so pressure will be high here. So fluid displacement will be more here, and pressure is low here because velocity is high. So this is your position 1, and this is your position 2, P1 and P2. Density of liquid, let us suppose the density of liquid is rho of L. rho of L. Okay. And suppose from here the distance is y1. This is y1. This is y2. And this difference is y. Okay. So y1 minus y2 is y. And we are saying that z1 is equal to z2 and y1 minus y2 is y. We can observe from the geometry. Okay. We know that our flow rate is how much? CD A1 A2 root of 2gh so far from the piezometric head difference, this h, okay, by root of A1 square minus A2 square. Now we have want this h to be in terms of y. What should be the relation? So from y we get the h, and from the h we get the discharge. Okay. So how we can get that? So again, we can apply the concept here that pressure is P1 here. So this is your point 1. This is your point 2. So P1 plus rho LGY1. If you are going down, the pressure increases. Then you jump from here till here because it's same liquid. So rho, and then you go above. So that is rho LGY in a minus because you are going above. So pressure will be decreasing. Then again it is equal to pressure P2. So let us see. Let us write the expression, that is P1 plus rho LGY1. Then you jump it, you go above, fluid is same, rho LGY2 is equal to your pressure P2. So from here you get the pressure difference P1 minus P2 is how much? So this is manometric liquid. This will be rho M. Okay. So this is rho MGY. My bad. I missed one expression. Rho LGY. Then we jumped from here to here, rho MGY, then above. Okay. Clear? Or any doubts? Okay. Rho MGY minus rho LG Y2 is equal to P2. So P1 minus P2 will be transpose all the properties here, rho MGY plus rho LG Y2 minus rho LG Y1. L is for the liquid which is flowing through the venturimeter, density of that liquid. M stands for density of the manometric fluid, which is inside a manometer. Okay, so this will be rho MGY. What is y2 minus y1? Just I wrote y1 minus y2 is y, so y2 minus y1 will be minus of y. So if I take in this way rho L G y, that is P1 minus P2. If I divide by rho L both sides, rho L in by G, P1 by rho L minus omega WL, so rho M by rho L minus 1 into 1. So this is your pressure difference. If Z1, Z2 would have been different, then it would be P1 by WL plus Z1 minus P2 by WL plus Z2. So this would have been your piezometric head is equal to rho M by rho L minus 1 into Y. And this is nothing but your piezometric head difference H, small h. So this is nothing but your H, which is now expressed in terms of the manometric head. So piezometric head difference of the flowing fluid is equal to manometric deflection. So right here, This is your piezometric head. Of flowing fluid, and this is your manometric deflection. Okay, manometric deflection. So you can write H in terms of W also. If you divide both by G, also H can be written as Wm by Wl minus 1 in terms of specific units, okay, into Y. Okay, you can write in both the ways. Even the venturimeter is inclined also. Still, my y in that case will be same only. Okay, let me explain what I want to say. The case like this, if my venturimeter is like this, suppose now my manometer will be attached like this at this position. Suppose my manometer looks like something like this. Okay, and this is your difference. That is suppose y1. In the first case y1. Okay, the flow is happening like this, and this will be rho of L. This will be rho of L. Or if my manometer, my venturimeter is like this. Kept horizontal as well. So my throat section. Then the case which we did right now, manometer will be like this. Okay, and this will be the deflection. Let us suppose our deflection is this is y2. Okay, again flow q, rho m, and rho l. Okay, so in the both the cases flow rate is same. Q1 is equal to Q2. Let us suppose that this is 1, this is 2. Q1 is equal to Q2. So what is Q1? CD, A1, A2. Both are of same venturimeter, same dimensions. A1, A2 are same. It's just that I have just inclined the one venturimeter and other kept as same. Root 2G, H1. Okay. The root of A1 square minus A2 square is equal to CD, A1, A2, root 2G, H2 under root of A1 square minus A2 square. So we are just left with all the thing cancels out, this cancel out, this cancel out. We are left with H1 is equal to H2, and H1 is nothing but rho m by rho L, y minus 1 into y1 is equal to rho m by rho L minus 1 into y2. This implies this and this term also get cancels out. We are left with y1 is equal to y2. So it doesn't matter that venturimeter is kept like this or that. If you have attached a manometer to it, the readings will be same. Also, the coefficient of discharge CD depends on three different things. Let me write here. CD depends on first Reynolds number, if it increases, that means your discharge coefficient will also increase. Okay. Next is surface roughness. That will eventually lead to losses in the venturimeter. Third is the area ratio. We have seen that A1 by A2 ratio. And we want that our A1 by A2 should be greater than 1 only, because A1 is the converging section and A2 is the throat section. Eventually this will be okay. All clear till here? Also, if I have a case like this, suppose, let us make a note here. If I have venturimeter like this, okay, and my manometer is differential manometer. You have seen what is differential manometer, what is YouTube manometer, all this. So if my device is like this, attached to it, and suppose my other side is inclined, then attached like this, suppose I have. So my deflection will be something like this. Okay, this is my rho of M, this is my flow rate Q, and this is my rho of L. Okay, now this inclination, let us suppose, has a length of L, and this, let us suppose, not this, sorry. Let us suppose, for simplification, let me make like this. Let us suppose we are having like this, and this to be a bit lower. Here, let us suppose. For simplification, I'm just making the diagram like that. So let us suppose like we have this deflection to be Y and inclined it is L. Okay. So from the geometry, we can say if this is at my angle theta, so from geometry, we can say that Y is equal to L of sine theta. Okay. And when we are saying what will be our flow rate value, CD A1 A2 root of 2GH by under root of A1 square minus A2 square. So if I use the expression of H is in terms of Y, this time my Y will be this value only. Okay, that is L sine theta. Okay, is it clear? Any doubts? No doubts? So we'll take a short break and then we'll start with orifice. Okay, let's come back to the concept of orifice meter. So why again it is a orifice meter is a used for discharge measurement. Okay, why it was has come into play? It was because when suppose venturimeter is a pretty much large device, but where if we want to have a flow rate calculation and we have space constraints, then we want a compact device which is nothing but a venturimeter, and it's also a pretty much cheaper compared to the venturimeter. So it's nothing but a circular plate with a concentric sharp edge hole at the center, and it is used to measure the discharge in the pipe flow and the tank openings. So because of the sudden obstruction in the device, there is a formation of a, we have seen a venocontractor formation happens because the flow have an inertia, and with the sudden obstruction happening, sudden compression or expansion when happens, you see there is a formation of eddies happens at that point, flow gets separated there and high losses occurs. That's why discharge coefficient value is required to be computed. Okay, and due to the formation of the contractor, CDS discharge coefficient is less compared when we have in the venturimeter. So venturimeter has around 9.96 value, whereas CD for orifice meter is 0.64. Okay, so let us write one by one all these points. Orifice meter. Used where space constraints less expensive device. It is a circular plate with concentric I hope I'm audible, right? Let's see. Yeah. With concentric sharp edge hole at the center. It is used to measure the discharge discharge in the pipe flow and tank openings. It is sudden obstruction device and due to sudden obstruction of flow, the velocity of flow increases suddenly and formations, and what happens are minimum areas forms, and due to the high inertia flow converges even after flow converges even after that and formation of vena contracta happens after vena contracta. After that, due to expansion, flow separation occurs and high losses occurs. So CD is less. This implies CD is less, ranging from 0.62 to 0.64. Okay. So let me first make the diagram of this orifice meter. This is a tube I'm having. Okay. There will be a sharp pointed edge, space circular. So it looks like something like a disc here, which has a very small hole like this. Okay. So I'll make that, don't worry. Sorry, I think it should not be like this. Very sharp and small. Okay, so flow happens with the flow rate Q and velocity V. Okay, let us suppose the diameter here is, these are three positions I'm having. First of all, the first position, the second position, third position. This shouldn't be a second position. Okay, this shouldn't be a second position. Let me make the second position data. Okay, so let us say our second position is towards this. Okay, as the flow was happening, and this is a diameter of the orifice, that is D naught, D orifice, DO, that is D orifice. So when flow was happening, the flow could happen somewhat like, because of the sudden obstruction, a formation of a small area happened. That is your vena contracta, and after that the fluid expanded. Okay, so here formation of vena contracta happened. Let us take some other color, this. Okay, and let us suppose this section is 3, C, section C for vena contracta. Okay, so here what is happening, because of sudden obstructions, eddies are forming. We have understood this concept of eddies in the last tutorial. Okay, and finally the fluid tried to expand. Okay, with the flow rate of Q. Okay, velocity will be same because the pipe diameter is same eventually, but there will be a pressure drop because of the presence of losses in the pipe. So initially the pressure was higher here, P1. Here the pressure will be dropping now because velocity is very high. the minimum pressure happens at PC. And then again, pressure increased because of the expansion, but not up to P1. So this is P2. Okay. P1, PC, and P2. All right, clear? Okay. And the diameter here is D naught, this much, of the vena contracta. And I'll make the this plate view as well. So this is something looking like orifice. And this is a orifice diameter. DOS, orifice diameter. Okay, DO is orifice diameter. And the area will be A naught of it. Okay. All right. And this distance is how much? Till where the vena contracta happens. So let us say it happens from a position of, from starting till this, the distance is generally half the orifice diameter. Okay, half the orifice. So minimum area in this setup is the area of the vena contracta, that is AC, and not the area of the orifice. So vena contracta area is much smaller than the area of the orifice. So minimum area is area of vena contracta. That is AC, and not area of orifice, that is A naught. Okay, first point. Because since Q1 is equal to Q2, this implies A1 V1 is equal to A2 V2. And since A1 is equal to A2, this implies V1 will be equal to V2 equal to V. So velocity is same, okay? But there will be pressure drop. But P1 is greater than P2 and which is greater than PC. Since losses in pipe, okay? Because of the losses in the pipe. Pressure 1 will be higher than 2 and minimum is at PC. Okay. And to measure the discharge, you will apply the Bernoulli equation between section 1 and section C. Okay. Section 1 and section C. And to measure the losses, we need to apply the Bernoulli between C and 2. Okay. Bernoulli equation, apply Bernoulli equation between 1 and C. Between 1 and C for. So if you apply, again, your relation will come out to be V1 square. I'm just directly writing into VC square by V1 square minus 1 is equal to H minus HL. Directly I'll write the expression. So from here, since we know that A1 V1 is equal to AC VC. So you can write V1 square by 2G. This VC by V1 can be written as A1 by AC square minus 1 is equal to H minus HL. Okay. So from here you will get your V1 square, that is 2G H minus HL by A1 square, and this AC, there is a coefficient of contraction will come. CC is nothing but AC by A naught. Where CC is your coefficient of contraction, AC is your area of vena contracta, and A naught is your orifice area. So you can write this AC in terms of A naught, that is A1 by CC A naught square minus 1. A naught square minus 1. Okay. Now you multiply both sides. So A1 V1 is nothing but A1. If you take A naught above, it will be A naught root of 2G H minus HL. Let us suppose I multiply and divide by root of H. And this H minus HL is already there. This H minus HL is already there. Okay. By, and I have multiplied and divided by H minus H, root of H. So here is multiply and divided by root of H. Okay. Also I multiply and divide by root of A1 square minus A naught square. Okay. Here also A1 square minus A naught square, and this remaining will be as it is going here. A1 by square by CC square A naught square minus 1. Okay. Now you'll understand why I'm doing this. So I will say this expression, this part is nothing but C, that is coefficient of orifice. Like similar, we had coefficients of Venturi. So this is nothing but C, that is coefficient of orifice. Okay. And this is nothing but equivalent to CD naught. That is C is nothing but equivalent to C of D naught. Okay, that is orifice. So you can directly write here, that is Q actual will be nothing but A1 A naught CD naught times, or CD times A1 A naught root of 2GH by under root of A1 square minus A naught square. Okay. And again, this is your piezometric head loss. Okay. And it happens in a pipe flow. Let us say it is okay. So your H is piezometric head difference. Okay. And this is the relation in a pipe flow. Okay. Again, we saw that CC is nothing but AC by A naught. Okay. That is coefficient of contraction, coefficient of orifice, and coefficient of orifice is nothing but equal to coefficient of discharge CD. Okay. And vena contracta can be measured experimentally using some screw mechanism as well, the pipe. And another scenario is, suppose you have a pipe like this with a certain compression. So what happens here? Again, a vena contracta forms and then it tries to expand. Similarly here, contracta forms and expand. So this will be your like A1, right? That is orifice kind of thing. Similarly, this I'm trying to make an analogy. AC, that is vena contracta, and this will be your section 2, that is okay. So here CC, how will you write the coefficient of contraction? It will be AC by A1. not A naught. Okay. And similarly, this kind of setup is measured this vena contracta. Suppose we have some screw kind of mechanism where my area of C, that is vena contracta, is happening. AC. Okay. These are your screw inside, and this is your pipe. Okay. And it is your measuring device, basically. Okay. Now there is a concept of experimentally how you will measure the coefficient of velocity of the orifice meter. Coefficient of velocity of orifice meter. Experimental measurement of coefficient of velocity of orifice meter. How we will do that? Let us see. So let us have a beaker filled with the fluid and have a small orifice towards the bottom side of the beaker. We have fluid filled with it. Okay. And there is some tap connection which is providing the head to maintaining the head to be constant. Okay. So that means H is constant. If I draw head is constant. Okay. I'll have a scale set up and I'll see because I'm measuring scale in X direction and a Y direction. Okay. With markings here. Okay. The flow is going like this. The velocity following some projectile kind of motion. Okay. This is your V actual velocity, which is through which the water is going out or fluid is going out. Let us suppose this distance is nothing but X up till where it went, and this distance up till where it went is Y. Okay, it is Y. So we know we have done this kind of concept where we have got a theoretical velocity was how much? Root of 2gh. From here, the theoretical velocity comes out to be, since V theoretical, we have already done this concept, that is root of 2gh. Okay. But we need to find out V actual. What will be V actual? There is one way from the coefficient of velocity or from the equation of motion. Okay. So suppose it's a free fall, which is happening. So V actual will be whatever distance happened in X direction to that of how much time it took. Okay. Other is equation of motion. If you apply Y is equal to ut plus half gt square. So in Y direction, suppose the velocity u was 0. Okay, kind of free fall. Only it was having an X velocity initially. So time from here will come out to be root of 2y by g. 2y by g. Now put this time here. So we get V actual is nothing but X upon root of 2y by g. Okay, so this is V actual will be is x root g by 2y. Okay. Now coefficient of velocity cv. So coefficient of velocity is nothing but cv. Okay. Your cv is v actual by v theoretical. So what is v actual? X root g by 2y upon v theoretical is root 2g h. Root 2gh. You know what is x, what is y from the scale. Okay. You know the value of g. You get the coefficient of velocity, that is x over root of 4y. 2 into 2 is 4 y h. Okay. Clear? Any doubts? So this is your coefficient of velocity. Very important. Experimentally, if you want to find out. Okay. We can write the discharge coefficient, coefficient of contraction, and coefficient of velocity relation. Since we know that, we can derive an expression that is, since we know that CD is nothing but coefficient of discharge is Q actual by Q theoretical, and Q is nothing but area actual into V actual by area theoretical into V theoretical. You know that V actual by V theoretical is CV, and area actual by area theoretical is coefficient of contraction. So this is CC into CV CD. Okay. So this is your relation, that is CD is equal to CC into C. Okay. Clear? Any doubts? Okay. Next device was flow nozzle. So I'll just briefly and quickly cover this. Flow nozzle. So it's also a kind of a scenario where we have a pipe, and inside this pipe we have a section like this. A gradual decreasing area. Okay. It's forming kind of a nozzle inside the pipe. Okay. So flow is happening like this. Okay. All right. So this is kind of flow which is happening. So again, we need to use a manometer here. One section is this. One section is this. Again, pressure will be high here. Rho m. This will be rho of L. This distance is y. So again, the relation of Q will be CD A1, A2. So this is your section 1. And this is your section 2, the area here. I think I should make till here. I should have taken section 2 to be the end of this. Okay. So this is your section 2. Okay. CD A1A2 under root of root 2GH by A1 square minus A2 square. And value of the CD is somewhere around 0.7 to 0.74. Okay. This is the approximated value. And this is a bell-shaped kind of scenario, bell-shaped. Okay, bell-shaped. Okay. Let's take a short break and then I'll join. Okay, let's come back. Let's come to the concept of pitted tube. Okay, you know that we have a pitted tube device. We have seen this kind of scenario. So we have the coefficient of velocity for pitted tube is 0.99. Okay, and it's highly accurate velocity measuring instrument. Highly accurate velocity measuring instrument. Okay, and it's basically used to measure a local velocity of the flow. So suppose I have a pipe like this, where flow is happening. It is at a pose from the datum like this. We have a piezometer attached to it. We have seen that pitted tube is always attached with a piezometer. Okay, it cannot be, because we need to subtract the piezometric head to get the dynamic head from the total head. Okay. And there is a pitted tube like this, a converging section. Okay. So let us say piezometric head is still here, and pitted tube total head is up till here. Okay. So it should be a static head. So this will be P by W. Till this position we have Z from the center line. This is also said. Okay. Pressure here is P, whereas pressure here at inside is E naught, let us suppose. Because sudden uh, stoppage has happened because of the presence of the obstruction. So this total head is nothing but P naught, that is your stagnation head, P naught by W, that is stagnation head, and the difference of this is your dynamic head. H is V square by 2G dynamic head. Okay, this is your dynamic head. All right. So here your CV is nothing but V actual by theoretical, that is root 2GH, root of 2GH. Okay, right. And also point to note here is that pressure at P naught will be higher than pressure at P. Okay, it will be always like this only because it has suddenly stopped, so velocity has become almost zero. That's why it's lead to a velocity head, dynamic head to the upper side. Okay, and pressure increase at that point of time. And suppose if you have a pitted tube attached with a manometer scenario instead of piezometer, so how we will convert this head in terms of that? So again, you have a pipe like this. Okay, I'm attaching a pitted tube scenario like this with a manometer. And sorry, the pressure at this position is higher on the right hand side because it has stopped. So this will be deflection less. So let us suppose that this is Y. Okay, here pressure was P, here pressure was P naught. Okay, this is rho M, this is rho L. So again, H will be rho M by rho L minus 1 into Y. And you can put this H to here. Okay, with this to get the coefficient of velocity. And point to note here is that when the pitted tube is moved across the pipe, not along, not along, not in this direction of the pipe, but across the pipe. So what happens? The level of the pitted tube will change. Either it will go up, down, depending on what's the moment. Okay. So pitted tube basically tells us about the total energy. Okay. The piezometric head plus the dynamic head. So when you are moving across, that means each streamline has its own energy. So that means you have a different psi values. That is the stream function values. A stream function have different values. That means if they are not same across, that means it's a rotational flow. Now you are able to understand that how the dots connect. Okay. So point to note here is that note when pitted tube is moved across the flow, level of it changes, the pitot tube changes, it gives total head, or you can say energy also, total head or energy. So each streamline has its own energy or head. Therefore, this implies flow is rotation. This implies psi1, psi2 are different. This implies rotational flow. Okay, rotational flow. Now let's come to impulse momentum equation. But before that, I want to just make a note of to the venturi meter side. If I go, if I have a venturi meter and if my manometer is attached, suppose the fluid inside the venturi meter is of lighter, not having a higher pressure difference. So in such scenarios, here, if I say here, the manometer will be inverted U-tube manometer. So I want to say if I have an inverted U-tube manometer like this, for less pressure difference scenarios, suppose this deflection is higher, this deflection, okay. Let's suppose this is this much is y, and this is rho m dash, not rho m. So in such scenarios, your h will be 1 minus rho m dash by rho l into y. Okay, for inverted manometer scenarios. Just wanted to highlight this point. Okay. Now let's come to impulse momentum equation. Whenever the Bernoulli equation or continuity equation fails, then we will use this kind of equation scenario. Okay, where the momentum is transferred. So suppose I have a fluid particle like this. Okay, which is having a mass I at initially. Okay, and it is moving with a velocity that is v initial. Okay, which is flowing inside a pipe, bent pipe, suppose. And because of the bend, the fluid will change its particle will change its motion. Suppose like this. And the final velocity become Vf and mass becomes Mf. Okay. So there is happening of that because of the fluid on the bent, the force will impulse will transfer, or you can say by the body on the fluid by the body. By the body on the fluid, or by the fluid on the body. Okay, one or another way. So let us suppose on this fluid, force acts like, suppose let us say R, because of which it changed the motion, and this is by the body, okay, or on the fluid, whatever you want to say. Or F will be in the opposite direction. Okay, so R is nothing but negative of F. So what is, since we know that F change force is nothing but change of momentum dp by dt. So change of momentum is fdt. So change of momentum can be written as fdt is equal to final momentum, that is mass into velocity of final, minus initial momentum, mass into velocity of initial. Okay, so F will be d by dt of m final v final minus m initial v initial. That means it is not the mass, it will be the mass flow rate. Okay, so m final dot v final minus m initial dot v initial, that is your net force. Okay, don't worry about the direction or who is applying on what. Just see that whatever the force comes out, it's by the body or on the body. And velocity has magnitude and direction. It's a vector quantity. Okay, so let us do one example here at how we can compute the value of the force. So let us suppose we have a scenario. So this is nothing but your impulse momentum equation, that net force is rate of change of momentum final minus initial. I have a scenario like I have a beaker connected to a pipe which has some vent. Okay, this is at some platform. Yep, at some platform. Okay, and fluid is up till some height. We need to study that at the bend what's gonna happen. So let us take this small section of the bend. Okay, so at the section inlet, the velocity is v because pipe diameter is same. So here also velocity will be v. Okay, towards the outlet. Let us suppose that this position is 1 and this position is 2. Okay, at the exit. So you can see these kinds of bends in your washrooms and all at your home. Okay, so pipes are connected through some bends. So at the bend, it's a very small change. So we say that the datum will be same at the bend. At the bend, we are assuming that there is very less change in the datum. So Z1 is equal to Z2, as well as velocities are equal because area is not changing for this case. And pressure will be also equal at both the section. Okay, so it's very small bend because bends are of very small height. Okay, bends are of very small height. Okay, we assume this kind of scenario always. Now let us, since bends are of very small height. Okay, bends are of very small height. Let us suppose we have another case like this, where we have a nozzle like this. Okay, because of this nozzle, suppose we assume a fluid element inside it at this position. Okay, this is your fluid element. So what are the forces which will act? One is because of fluid back, there will be P1A1. Okay, acting on this fluid element because of the fluid behind, and there will be a pressure force here also, P2E2, because of the presence of the ambient particles. Okay, velocity will be like this, V1 in this direction. Okay, and after this getting out of it, V2, because area of the cross section is changing. This is your fluid element. Okay, fluid element. And because there is a changing cross section, some bend is happening, so there will be some force. Let us suppose the direction of the force. We are supposing, even if it's wrong, the sign will come out to be different. So let us suppose the force acting by the bend or by the body on the fluid element is in this direction, that is F. This is your bend force. Okay, this is your, so only horizontal force will be there because vertical forces will balance out. How? I'll make a projected, a zoomed kind of scenario. So I have a force, net force, which is like this, F net. Similarly like this, F net. So there will be horizontal force, FH, FH, and the vertical force, FV, FV. So net force is only horizontal lift. Okay, that is your FH, because vertical forces cancels out. So we apply the impulse momentum equation. Sorry, just have to put my tab on the charging. Hold on. Okay. So apply the impulse momentum equation for a particular direction. Let us say I think this will. So net force in the x direction is nothing but change in momentum m final v final rate in x direction minus m initial v initial rate in x direction. Okay, so in the x direction, what the net force, what forces are acting? So that is P1A1. Let us suppose this direction is positive. So P1A1 minus P2A2 minus F horizontal. Okay, this is the net force. What is the final velocity? So mass flow rate is rho into Q, rho AV, into what is final velocity? That is V2. VFX is V2 minus rho Q. What is of initial velocity? V1. Okay, rho Q V2 minus rho Q V1. So your net force, that is H, horizontal force, will be P1A1 minus P2A2 minus rho Q V2 plus rho Q V1. This is your on the fluid by the body. If it would have been, we assume that on the fluid by the body was this direction. If it would not been in this direction, if it would have come out to be negative, and that means in actuality it would have in this direction. But from the physical idea we have, from the experience, we can see that eventually on the fluid element, it will, by the bend, the force will act like this. So don't worry about the direction. You can assume any direction initially, and in the final, if it comes out to be negative, you change the direction on the fluid by the bend. Okay, so it's always applicable over the gauge pressure, remember, because in absolute pressure the atmospheric pressure will cancel out. Okay, next scenario, suppose I have a bend like this. Next example. Okay, so again we assume a small element of fluid. Okay, again P1 A1 will be acting like this. There will be some velocity of the fluid P1. There will be velocity of the fluid, that is V2. Okay, there will be pressure which is acting by the above fluid on the element, that is P2A2. Okay, in this direction. There will be a net horizontal force by the bend here. Let us assume this is the direction Fx, and by the bend here, that is, let us suppose the direction is Fy. Okay, on the fluid element by the bend from the downside and from the right side. Okay, so net force, let us suppose, balance in both the direction. So F net in x direction is nothing but rho Q Vfx minus rho Q Vix. Okay, initial and final. Clear? So what is net force in x direction? We assume that this and this are positive. Okay, P1A1, there is no from the right hand side, only minus f of x is equal to rho Q, final velocity is 0, minus initial velocity is rho Q V1. So f of x is P1A1 plus rho Q V1. This is your net horizontal force on the fluid, okay, by the bend. Next, on the fluid. Okay. Now in the y direction, F net in the y direction is rho q v final y minus rho q v initial in y direction. So what is y direction? Initially, no y. Final, it is P2A2. That is minus P2A2 because we assume downward is negative. And Fy is acting, we assume it's positive. Final velocity is rho q P2 minus 0. So Fy comes out to be P2A2 plus rho q P2. Again, this is on the fluid by the fluid. So you got the values of net force on the fluid because of presence of the bed. Okay, any doubts? Now we will proceed to the viscous pipe flow or the laminar pipe flow. This will take a short break, then I'll join. Okay, let's come back to viscous pipe flow or laminar pipe flow. Viscous pipe flow, or you say laminar pipe flow. Okay. So when the fluid is flowing in form of a laminars with negligible mixing, we say that it's a laminar flow. Okay. So what are the features of a laminar flow? There is no slip at the surface, that is velocity profile approaches at the surface, right? But in turbulent, velocity profile is nothing but approaches up to some sublayer thickness, laminar sublayer thickness, and it forms a linear profile. Okay, there is negligible mixing between the layers in the laminar flow. Flow follows Newton's law of viscosity, and head loss due to the friction is proportional to the first power of the velocity in the pipe flow. FL, first power of the velocity in the. Okay. So we'll see all these head loss, friction, everything. So let me write here, when fluid flow is in form of lamina with negligible mixing, is known as laminar flow. What are features of laminar flow? First is no slip at the surface. That is velocity profile. Approaches at the surface. But in turbulent flow, velocity profile approaches up to laminar sublayer and laminar sublayer has linear profile. Okay. Then there is negligible mixing between the layers in laminar flow. Then flow follows Newton's law of viscosity. Also head loss due to friction. Is proportional to first power of velocity in pi flow. Okay. So that means whenever the flow is happening, suppose over a flat plate with a very high velocities. So initially, because of the no slip condition, there might be a chances of having a laminar sublayer, but there will be a transition from laminar to a turbulent scenario. Okay. If the flow is totally laminar, then we say that only the form will be laminar and all these features of the laminar flow will follow. Okay. But if it's a turbulent, so transition will happen. Okay. And where eddies will form, mixing between the layers will start happening. So there is a transition zone where we say a critical Reynolds number play a role which decides the flow is turbulent or laminar. We have talked about this in our previous tutorial. So if my flow has a Reynolds number greater than that critical zone, then it's a turbulent flow. If it is less, then it's a laminar flow. Okay, so we come to the concept of critical Reynolds number. That is REC. Okay, so below which the critical Reynolds number REC, below which flow is fully developed laminar, and after which fully developed turbulent flow okay, to encounter transition effect. Okay. So what do I mean? Suppose I have a flat plate like this. Okay. Flow is happening here with some free stream velocity that is u infinite. Okay. So initially, if the flow is laminar, so a boundary layer will form. No slip condition will also be there at the surface. Newton's law of viscosity will be formed. Okay. Then there will be some transition zone, suppose like this, of some thickness. And after that, if flow becomes turbulent, a rapid mixing happens, because of which the layer boundary of the layer becomes more large compared to the laminar scenario. Okay. So this transition zone is the zone where critical Reynolds number plays a very important role. Okay. And inside this, the critical Reynolds number value for a flow over a flat plate, suppose we say a center line value of the Reynolds number is your critical Reynolds number between this. Okay. So for the flow over the flat plate, it is 5 into 10 to the power of 5. Below, the Reynolds number is 2 into 10 to the power of 5. And above, the Reynolds number is 1 into 10 to the power of 6, or any value you can have above 5 into 10 to the power of 5. Okay, this is a real system scenario. Basically, fluid was flowing like this, but in the transition zone, some eddy formation started happening because of the turbulent mixing of the layers. Okay. Because of the mixing between the layers for the turbulent flow. And in turbulent flow, the velocity profile approaches up to laminar sublayer. So there is some sublayer. So because of the transition which is happening, there is a formation of a laminar sublayer. So from here that it started till, suppose till here, and there is some thickness up to which in the turbulent flow a laminar flow will condition will follow. That is your till here. That is your laminar sublayer. Laminar sublayer. This is your laminar sublayer inside a turbulent flow, up to which the velocity profile follows. And the thickness of this laminar sublayer, let us suppose the thickness of the laminar sublayer is their experimental value which has been derived, experimentally defined. Delta is delta dash 11.6 new kinematic viscosity by wall shear stress, that of density. Okay, that of density. And this is your laminar sublayer thickness. Laminar sublayer thickness expression. Okay. All right. Now, if we have a pipe flow, for a pipe flow, this was a flow over a flat plate. But if I have a pipe flow, what is the value of critical Reynolds number? If Reynolds number is less than equal to 2000, then it is laminar. And if greater than 4000, it is turbulent. Laminar. So anything between 2000 to 4000 is a, let us suppose a mean of it, 2300 is a value which comes out to be, not a mean, 2300 value is a critical Reynolds number for flow through pipe, 2300. For open channel flow, what do I mean by this? So this is a pipe flow. Okay, the flow happened completely. For an open channel flow, it was like this. That means my fluid is up till somewhere till here, not completely filled. Okay, it can be through a pipe, through any cross section. Okay, so for this, the critical Reynolds number is 500. Okay, and flow between the plates. For flow between plates, not plates, parallel plates, you should say. Orientation also matters. The critical Reynolds number is 1000. Okay, critical Reynolds number is. Okay, now coming to the very important equation. So far we are dealing with the Euler's equation, where pressure force, gravity force was there, giving us the total net force, mass into acceleration. But when viscous force also comes into the role, then a Navier-Stokes equation plays an important role, which is a fundamental equation for viscous pipe flow. So let me write Navier-Stokes equation is the fundamental equation for viscous pipe flow. Okay. And what are the applications of this Navier-Stokes equation? NS equation. First is laminar flow or flow through viscous flow through circular pipe. Laminar or viscous laminar flow, or we can say viscous flow through circular pipe. This is also known as Hagen-Poiseuille equation. We will derive this equation, don't worry. Hagen-Poiseuille equation. Okay. Second, between the parallel plates, laminar flow or viscous flow through parallel plates. Let me just shift it here. Laminar flow, viscous flow through, not through, between parallel plates. And this kind, which is stationary, plates are stationary basically. So this is your plane Poiseuille flow, also called as plane Poiseuille flow. Okay, and third is viscous or laminar flow between parallel plates, but one is moving. So relative motion is there. One is stopped, one is moving, or both are moving with some relative motion, different velocities. Between parallel plates under relative motion. Okay, and this kind of flow is called as coed flow. Okay, this is known as coed flow. Okay. So there are two scenarios here. One is shear stress distribution. If we start with the Hagen-Poiseuille flow, there is a shear stress distribution, velocity stress distribution. Okay. From that velocity stress distribution, we will get the mean velocity. From mean velocities, we will get the discharge. Okay. All right. So let us do one by one. Then we'll come to the plane Poiseuille. Then we'll come to the coed flow. So let's start. Shear stress distribution in circular pipe flow. Okay. So Bernoulli equation won't work here. Navier-Stokes will work because Bernoulli equation work for non-viscous flows. So here are some assumptions we need to follow. Again, it won't be inviscid. Viscosity will be there. So first is steady flow. Uniform flow. The flow should be uniform. Third is it can be either turbulent or laminar, but should be fully developed. Can be laminar, oh sorry, should be fully developed. Okay, these are the three assumptions. So suppose I have a pipe like this. I have a fluid element inside it. Let us assume I have a fluid element, cylindrical fluid element I take. Okay. There will be a pressure force which will act from the left hand side. Pressure into area, that is P into pi r square. Let us suppose r is the radius of it, fluid element. And here on this side it will be E plus dou P by dou X dx into pi r square. So let us suppose the length of this fluid element is dx. Okay. And there will be eventually a shear force which will be acting opposite. Because fluid is flowing like this. Okay. This is your x direction. Okay. So fluid is also flowing like this. Okay. So from the Navier-Stokes equation, it says that pressure force, viscous force, gravity or body force is nothing but mass into acceleration. What is along the streamline if I say V dou V by dou S plus dou V by dou T. So we have assumed that it is uniform and steady. So this whole term become 0. We assume that there is no gravity force. So let us take this is also 0. So we are left with Fp plus Fv is equal to 0. What is pressure force? So it is change in the pressure, that is minus dou P by dou R. We assume that this direction is positive. Okay, this direction, dou P by dou R, dou P by dou X dx into pi r square. And what is shear stress? That is also acting in the opposite direction, tau into what is the area? 2 pi r circumference into dx, because it's acting over the whole length. 2 pi r into dx is equal to 0. So from here, the shear stress will come out to be minus dou P by dou X into R by 2 into R by 2. This is your shear stress expression for a flow from a pipe. So it is valid for both laminar or turbulent. Okay. So if I say my it is a fully developed, so shear stress is directly proportional to the radius. Okay. So this says that shear stress is directly proportional to radial direction. So how if I want to form a shear stress profile, how will it look like? It will, suppose I take a section like this. Okay. So my shear stress profile will look like this. With increasing R, shear stress increase, and it's evident actually, right? In the opposite direction. Why? Because of the no slip condition. This is my flow. Okay. Right. So as R increases, if my R direction is like this or that, it depends. So my R direction is going from here. As R increases, my shear stress increases. Okay. And here, this is a line of constant pressure because my flow is fully developed now, constant. This is a scenario of fully developed. Okay. So for this section, with respect to R, we are seeing. Okay. So at R is equal to R, capital R, that is the pipe radius, my shear stress is maximum, that is tau wall. Okay, so tau wall will be minus dou P by dou X into capital R by 2, capital R by 2. And if you observe the dou P by dou minus dou P by dou X, so as X increases, if I say as X increases, that means dx is greater than 0 when I'm saying, and dP is less than 0 because pressure, because of the presence of the losses, so pressure will reduce. If I suppose this is my section 1, section 1 and section 2. So since P1 is greater than P2, this implies my dP is less than 0. So therefore, dP by dx is less than 0. Okay. So this implies minus dou P by dou X is greater than 0. So this is a positive term. So my shear stress will also be positive. The assumed direction is correct. Okay. Is it clear? And if I say my pipe is inclined, then instead of, so I'll write, if I have an inclined pipe, okay, this is suppose making angle theta. This section suppose is S, Z section from position of 1, position 2, okay, all right. Let us assume that this much element is B of S, okay. This is at Z, this is at Z plus dz. So shear stress is minus dou P by dou S. So P will be P plus rho gz this time into R by 2. So it will be minus, what will be pressure difference? P2 plus rho g Z2 minus P1 plus rho g Z1 by change in displacement into R by 2. So if it's a horizontal case, your Z1, Z2 is equal, and S2 minus S1 is X2 minus X1 basically. Okay, I think we'll do the velocity distribution in the next tutorial on coming Tuesday. So I hope everyone has understood so far. So you'll get these PDF notes and the recordings through NPTEL team corresponding to my name. All the links will be there. If you are new to the channel, directly watching from the YouTube, so my YouTube channel name is it's NPTEL with Varnit. So my name is Varnit Kapoor, and every video description corresponding to that course, you will find the Google Drive link where you will find the PDFs of all the. So I think we can end the session here. I'll see you in the next session. Bye-bye.